All right. So in the previous video, we saw the operating principle behind this parallel plate actuator uh, based on the electrostatic actuation and capacitive sensing, and we see that when this top plate gets displayed by a distance x, this spring, which is a mechanical spring given by spring constant in Newton per meter, gets stretched, and its original value, or say nominal value, gets altered, which can be equated by this expression, that is K effective equals Km plus Ke. So we'll see that how to derive an expression for this spring constant of this structure. So this system can be can be represented by a physical system. This is a physical system and can be represented by a mass spring a damper system. Simple 1 degree of freedom mass spring damper system, such as this. So as we can see over here, there is a proof mass M, which is suspended by this spring indicated by K. So and of course, when there is a movement of this proof mass, uh, it'll have certain velocity that gets opposed by this damper over here. That's why that's indicated by C. It's called as damping coefficient or damping constant. So since these are the elements mass, spring and damper, they are associated with their respective forces. So we'll see that. So when proof mass experiences a force, it could be a mechanical force, or such as in piezoelectric crystals, or it could be electrostatic force indicated by Fe. And as we saw in the previous video, in case of parallel plate capacitive actuator, that force was electrostatic, so which will displace this proof mass from its original position by a distance x indicated over here. And when there is a movement of this proof mass in a given direction, this spring will offer or exert another force called as restoring force of this system, and that is indicated by spring force or restoring force, equals K times X. uh, uh, and similarly, the damper also experiences a force indicated by Fc, that equals C times a velocity x dot. So note the direction of these forces. They are opposing the applied force right over here, that is Fe. And this is a 1 degree of freedom proof mass spring and damper system, from which we can derive some expressions for the spring and all. So as we can see that when this proof mass moves down due to this force, this spring gets stretched. This original value in Newton per meter will get altered, as we've also seen in this diagram. So when this top plate is getting displaced by a distance x, this spring is getting stretched over here, indicated by this new representation. And then the effective value of this becomes Km, which was the original, plus Ke. So Km is called as a mechanical spring constant of the system, and Ke is called as the electrical spring constant, which is introduced into the system because we applied a voltage difference across these two capacitor plates. If we turn this off to 0, this Ke is no longer into this equation, and the original spring will come back to its normal value, because this plate, which has been displaced to a distance x indicated by this green line, is the new position of this top plate, will go back to its original position right over here. So that's the so when there is a force, you have movement. When there is no force, there is no movement. So that is how it works. So coming back to these proof mass spring damper system, what we can do is that the net force, that is the total force, we can write it as F equals ma, where m is the mass and a is the acceleration. So acceleration is basically a double derivative of the displacement, which is x. So that's why we can write it as a F equals m times d square x dt square, and where the acceleration is basically a double derivative d square x or dt square, and we can also write it as a x double dot. So x is a position, x dot is a velocity, x double dot is an acceleration. So we write here velocity v, that is x dot, which is a single derivative of displacement, that is dx over dt, and x is the displacement from its equilibrium position. So what we can do is we can sum these forces, and in this figure all these forces can be summed over here based on their directions, and one can get an expression like summation of forces equals Fe, which is the applied force, minus Fc, which is the damping force, minus Fs, which is the spring force. Note the directions, they are negative because that they are opposing the applied force, and the summation is equal to Ma, indicated over here in this expression over here. And then this equation can be rearranged in this form, where we can write Fe equals Fc and Mfs goes to the right hand side of this expression. So M as it is, A which is over here, that is a value of A is d square x over dt square, and plus this C into dx dt is the damping force, plus kx is the restoring spring force. So that is the expression for the net applied force for the single degree of freedom system. So if the system has no damping, let's say there is no opposition to the velocity of the proof mass, so we can keep this Fc equals to 0. So for undamped system, we don't have this force over there, and for a static case, it means when the x is independent of time, it's just like you apply a DC voltage as shown in this figure. You don't have a AC, the electrical combined electrical load is no longer AC plus DC. We only have a DC component over here, so it will just displace this top plate by distance x. So that's it. So it's a static case where x is not dependent over time, and we come back to this expression, and we see that the x is independent of time, and we can write, and we know that the restoring force is equal to k times x. So in case of parallel plate capacitive actuation, what we can write here, the effective spring force, that is Fs effective, becomes K effective times X. So just note these two expressions, this one and this one. So now there is a displacement, so Km becomes K effective, right? This is basically a Km, as we've seen before. And K effective has the value of Km plus Ke, where Km is a mechanical spring constant in Newton per meter and Ke is an electrical spring constant due to application of the DC voltage into the system. And how to derive an expression for Ke then? So we can get an expression of Ke by differentiating the applied electrostatic force Fe with respect to X. So we know that what is Fe is basically half times epsilon A d minus x whole square v square. We can recall this expression over here, that we have done this expression. We see that there is a potential energy stored in the capacitor given by this one, and in the previous video we saw how to derive an expression of associated net electrostatic force. By differentiating this equation we get an expression. So that is a expression for the force. So coming back to this one, we differentiate this, so this becomes epsilon A into v square, this top equation, over 2 d over dx 1 minus d 1 over d minus x whole square. So it's a simple differentiation. We can get an expression as total final expression as minus Ke equals minus epsilon A over 2 in bracket d minus x whole cube v square. So we note here that this Ke has a negative effective value. This Ke has a negative effective value. So if we take a look at this one, if the Ke has negative effective value, the effective spring constant goes down. Original, let's say it was a 10 Newton per meter, and the spring is now, electrical spring is now 1 Newton per meter, but it has a negative effective value, so it is minus 1 Newton per meter. So K effective becomes 10 minus 1, 9 Newton per meter. So how to understand that as a physical representation? So this spring originally was 10 nano Newton per meter. Due to application of voltage, it has reduced its value. So looking back to this diagram, we see that the Km, that's the original one, because of the introduction of the spring application of the DC voltage, spring gets stretched and the effective value is reduced because the Ke has a negative effective value. So what we can say is that when the Ke is a negative, Ke has negative effective value, spring gets stretched and effective spring gets stretched and the effective value is reduced. If the Ke has positive effective value, the in that situation spring should get compressed. So this plate over here will not get displayed down, instead it will get pulled up over here, somewhere over here we can see that. So the spring, instead of extension, it will get compressed. So we can understand that in a later lecture. So that is the effective value. Now this action is called as spring softening because spring has stretched, and we also can see that its impact on the resonant frequency if it has to operate as a resonator. We can see that later. And if we assume that the displacement in this expression is much smaller than the original gap d, then the effective value can be equated as Ke equals minus epsilon A over 2 times d cube into v square, and v is always an combined electrical load, which is a combination of VAC plus VDC if the structure operates as a vibrating element or a resonator. Now we can derive an expression of Ke at the drive frequency just the way we derived over here an expression of force at the drive frequency right over here. This expression we derived from this equation. We can derive this equation as we have seen in the previous video. Similarly, we can derive an expression of Ke at the drive frequency, which is given by Ke equals minus epsilon A over 2 in bracket d minus x whole cube. In bracket we write this v square, we expand and write it as a v square AC plus v square DC plus twice VAC DC. And now we are interested into this frequency because at the drive frequency, okay, so we just cancel out, neglect these two terms, v square AC and v square DC, and final expression of Ke at the drive frequency becomes minus epsilon A over d minus x whole cube in bracket VAC into VDC. If we are interested in deriving expression of Ke at twice the drive frequency, which is due to this term, as we've seen in the previous video, we can also get an expression of net electrostatic force at twice the drive frequency. Similarly, we are now getting an expression of Ke at this frequency, so we can again write back Ke equals minus epsilon A over 2 in bracket d minus x whole cube v square AC. So what is this v square VAC? VAC is basically a sine wave with a certain amplitude and a certain frequency, which is basically a harmonic load to this physical system, and which can further be, so now this is v square AC, so this term is Vm square sine square omega t. So where Vm is the amplitude of the sine wave and omega is the angular frequency in rad per second. Remember, the negative sign is still there, so we keep on solving this. This takes the form of minus epsilon A over 2 in bracket d minus x whole cube Vm square, and sine square omega t can be expanded as 1 minus cos 2 omega t over 2. Finally solving this, the expression of Ke at twice the drive frequency goes as minus epsilon A over 4 in bracket d minus x whole cube Vm square in bracket 1 minus cos 2 omega t. So that's the analytical derivation of the electrical spring, what we can get. So for the linear dynamic case, if the x is now, because now you have introduced a harmonic load given by this VAC term, x is a time dependent. So in that situation, the expression of this effective restoring force will be written as Fs effective, which is a function of time, that equals K effective x into x of t. Fs effective, which is a function of time, equals K effective into x of t. And yeah, so this is how